So whenever you're ready, go ahead.
I think they're just having some issues getting it to load. Somebody's Chromebook is very slow today, but I think they're just about ready. I've been keeping them waiting long enough.
Okay.
All right, I think we have a solution. They're not able to unmute for some reason.
Oh, weird. Okay, that's all right.
Yeah, that's fine.
All right, good. All right.
Okay, yeah, so this is our Moon Asteroid 101 project where we analyze 3 images of the moon and 3 images of the asteroid. My name's Alion.
I'm Faizan. I'm James.
I'm Samiksha.
I'm Matthew.
I'm Sophia.
I'm Anastasia.
So for the first image, the circles indicate lunar domes, and these are formed by the moon's internal volcanicism. And volcanoes extrude layers of lava slowly, and they dry, forming domes.
So these domes form gentle hills as seen by the shadows formed by light coming in from the right. You can see how some hills are steeper than others by the depth of the shadow. The smooth and the surrounding surface, they're newer and have less damage from asteroids.
For here, you can see with the blue lines, they represent the mounds, and how they are formed is by the lava cooling after earlier volcanic activity in the moon's early life stages. And in the red, smaller mounds pretty much formed by the same way as the larger mounds.
So for the moon image number 3, I'm just going to be talking about the geological features of this image. So first, the circles represent the sinus rills because they begin at the crater and then kind of go away from it, and then they eventually disappear from the surface. The red arrow shows a simple crater because it doesn't have a peak in the middle, but the edges are bowl-like. Yeah. No.
There you go.
Okay. Also, this is image 3 continued. So the sinuous rills form from the lava channels and collapsed lava tubes, as seen in the earlier image. And they begin at the crater and curve and twist away from it. And they are younger than the lava tubes shown in image 2 because they formed after it from the lava tubes. And the crater formed from an impact from a small meteorite or explosion because it is a simple crater. And you can tell it's a simple crater because it's bowl-shaped crater and there's no peak in the middle, and it has a raised rim because there were less fluid motions of the rock during the impact because there was less force since it was a smaller impact.
So we'd now like to open up for questions for the moon.
Okay, great, thank you. Go ahead and go back to the first image, and while you're doing that, I'll just say a few things. So good job, good. I like how you annotated stuff, right? So you circled things, you pointed to things, you gave colors, you told us what those colors represented, what you were looking at. That's great. One thing I would suggest though, given what the text you have and what you talked about in your slides, there's a lot of text. You weren't necessarily reading from your slide, but what you were saying was also on your slides. So just be careful with that, and the reason I say that is, and this is for the future, when you have a lot of text on a slide, people in your audience will be looking at that text because they're assuming this needs to be read. And when they're doing that, they're not listening to you. I don't care what anybody tells you. You cannot multitask reading something and listening and understanding both at the same time. Your brain does not work that way. Unless you're just evolutionarily superior. So just don't worry about putting a lot of text on the slide. Having text to say, if you have a green circle, a green or a red circle equals crater, or a green arrow points, stuff like that. A legend, basically. If you have a legend, that's cool. That's perfect. Just careful with a lot of text because it's just basically distracting. When you were looking at this picture and deciding what you see here, how did you make the decision that you were looking at volcanic domes?
Okay, can you hear me? So we decided that because from like the smoothness of each mound, it was more likely to be formed by volcanism, because like as lava would cool, it create like smooth mounds, which is what's seen in the image.
Okay. What makes something rough then?
I mean, I'm not sure, but I imagine it'd be like steeper hills and like sharper angles for the mounds.
Okay. Okay. That's fair. So everything you say here in terms of like, you know, basically like the general shape of them, talking about shadowing and what that does and how you can interpret the, you know, steepness of them. That's all great. But what if I told you that the sunlight in this picture is coming from the left? Would that change how you identify the features that you circled?
Yeah.
How would it change?
I'm really not sure.
Well, it could change our idea of what rock it actually is. So that would mean that it's not necessarily a reflection, it's a darker rock, which could change how it was, our idea of how it was formed.
Okay, so follow up. Would you still say they're hills or domes? Would you still say that?
I don't think so.
Then it could be a crater, right?
Sorry, the way you inflected your voice on that just tickled me. Okay, yeah, these are actually everything you see in this picture is a crater.
Right.
So I purposely did not give sun direction in any of these pictures. I did it on purpose. I just like to hear what you all think and your reasoning for it. And I'll tell you, just about everybody, every year of this program thinks these are volcanoes or domes. But everybody's reasoning for it is always the same. And it's good reasoning, right? There's just that one really key piece of information you're not given. And that's on purpose. So don't feel bad. That's just me being mean, I guess. But that's about as mean as I get. Okay, good job. I'll just point one thing out before we move on to the second picture, second image. The bigger circle in the kind of the upper right of the image,
Yep.
do you see at about the 1 or 2 o'clock position, do you see that brighter kind of speck? It has kind of like a dark line extending away towards the left. Yeah, right there. That is the lander from the Apollo 12 mission. So in November of 1969, when Apollo 12 landed on the moon, that's where it landed. And those dark linear streaks or lines that you see coming away from it, and if you look, you can kind of see them all the way around that crater. Those are astronaut footprints. They're astronaut footprints, and they had this like this cart, this two-wheeled cart that they hauled around tools and things in. And so you're kind of seeing the tracks from that too. But they're all just mushed together into like one thing because it's, you know, those are small things compared to the overall, compared to everything. So that's kind of cool. I mean, and that piece of hardware that's left behind, that was, so when they got off the moon, they got back in the lander, but only the top half of it actually launched off and brought them back up into lunar orbit. That part stayed behind. That's the part with like the 4 legs on it that you might have seen in images. But anyway, that's the Apollo 12 site. Alan Bean was one of the astronauts on that mission. He did some paintings. He was taking art classes while he was training to go to the moon. And then when he got back, he did a lot of painting up until like the time he died just a few years ago. Pretty cool stuff. So Alan Bean, ALLANBEAN, look him up. See some of his artwork. All his art he does is based off of his experience of being on the moon, which is pretty cool. Okay, next picture. Okay, so this picture is interesting. So again, all the circular things you see here are craters. And one thing I'll point out is you talk about the blue lines. What I see are like almost black, dark green, almost a black. So that's just something to remember. I mean, the red looks red to me. The green outlining that linear thing with the bend, that looks green to me. But the other things look black. Just something to think about. Maybe just use some basic white, red. Anyway, so they're all craters. Did you say anything about what's between the green lines? I don't remember hearing that.
I don't think so. No.
Okay, so what's between the green lines? Why did you point that out?
Well, originally it was pointed out to us that it was a mound, but
Okay. So this is not a mound. This is a rill. This is part of a rill, so it's a depression, right, in the ground. It's a vacant or an old lava channel, lava tube that the top of it then collapsed at some point after the lava was running through it. This, again, it didn't give you a sun angle, but even if I did, it's still tricky because this sun angle is almost directly overhead. So there's very little shadowing, as you can probably notice. So it's very, very difficult to tell what you're looking at in this picture. If the sun angle had been lower, which there are other images of this area with a lower sun angle, all those features, those craters become much more circular. They look which they are. They are circular. They're just not in very high sun angle. So sun angle is very important when you're looking at planetary surface images of planetary surfaces. Okay, going to the third one. And this here is one of my most favorite images ever, just because there's so much geology going on and so much you can talk about in terms of geology, particularly with the moon. You can talk about relative age dating. If you consider the four things you see in this picture, the rill, as you pointed out, the simple crater, as you pointed out, the darker area the rill is cutting through, that's mare, and then the brighter grayish wider areas, that's highlands. There's 4 different kind of geologic units you see here. So you can talk about what we call superposition in geology, which is how old things are relative to each other based on looking at just the order they would have formed. Have you all done that kind of an exercise before?
Neuroscience. Oh, that's super.
Yeah.
Yeah.
Okay.
Yeah.
So real quickly, looking at this image, I'll just mention the top green circle, about the 3 o'clock position on that oval, where it crosses the rill, that little bow, that bend you see in the rill, go down a little bit. There, that bow, that bend, that's the area from the previous image.
Oh.
Oh wait.
And I'll point out that just to the right of that bend a little bit, that's where the Apollo 15 mission landed in 1971. So real quickly, and then we'll move on to the next presentation. But considering the mare, the dark lava plain there, the highlands, the mountainous areas, the rill, and the simple crater, can you tell me how would you order those in terms of oldest? So oldest to youngest, which feature of those 4 is the oldest down to the youngest? Can you rank those for me real quick? Anybody?
I think I would say the rills definitely formed after the crater, since they form they touch the crater and then go out from there. And then I would say the surface, the Mar, then the highlands, then the crater, then the rills, because it doesn't look like the crater is has a lot of damage to it from other things forming on it.
Okay. Anybody else? Any other thoughts?
I'd say that the craters the youngest, the highlands are the oldest, and the rills in between.
Okay. What about the mare?
The crater's on top.
I say the mare is older than the rill, but not as old as the highland.
Okay. So here's how you would do this. Highlands are the oldest. And we know that because the highlands were the original crust of the moon after it solidified. Then you have the mare. You also know the mare is younger because in the highlands, because it's like flowing into it, it's breaking up the highlands. Then the question is crater or rill, because you can't have a rill without mare. The mare has to be there first. So it's the lava that then cut through it, and then eventually the roof collapsed, and now you got this rill. There's actually just one rill there, and it's being interrupted by the crater. So in this case, it's highlands, mare, rill, crater. Okay. All right, let's go ahead and get to the next presentation because we're running out of time. Good job. Good job, though.
Next presentation.
Yeah, it's the same slide.
So this is the first image for the asteroids, and the red circles are formed from collisions, and over time, asteroids collide with other debris and form these irregularly shapes. Another way these lumps are formed is the accretion process, a process in which small dust particles merge together from gravity. These lumps can range from being very recent to 4.6 billion years ago. There are various processes that form these lumps, therefore they can be either recent or very old.
Okay. Many craters on the surface suggesting the asteroid is quite large and has been hit by many space debris.
The mid-top portion of the asteroid contains more craters than the bottom, suggesting that the bottom portion of the asteroid is actually younger. And the red circles indicate overlapping craters, with the left crater being newer than the right crater.
Asteroid image 3. So there's smoother with small impact rocks that are compared to other asteroids. The surface consists of a deep layer of fine dust, and it also has a taxonomic type S, which is type S or a silicate asteroid, which is located in the inner belt. It also has the small impact rocks that are seen on the surface, and this is a result of foreign objects hitting the surface when the asteroid was more magma than solid.
All in all, there are many different aspects of moons and asteroids, from the way certain things form on either celestial bodies, how recent they've been formed, and how they were formed. The giant impact theory poses a good explanation for the moon, and the accretion process explains how asteroids are created.
I would like to now open up to questions.
Hey. Yes, historically, this presentation really does not take very long compared to the moon one. So let's take a look at the first image. This is of an asteroid called Itokawa. About 20 years ago, the Japanese space agency sent a spacecraft there to collect samples and brought it back. So we actually have pieces of this asteroid back here on Earth in collections. Some are here at Johnson Space Center. I think most of them are in Japan. So these asteroids like this are what we call rubble piles, because they're just exactly that. It's just a collection of rubble, just being held together by gravity very loosely. Though, if you sent a spacecraft like we did, the Japanese did, and if you touch it, push a spacecraft against it hard enough, it'll just start coming apart, and then it'll just kind of come back together again. It's really not something we experience in our everyday lives, but that's what would happen. Of course, lots of boulders there that range in various sizes, all the way down to those smoother areas, which is just like dirt and dust. Those big, huge boulders that you see there. I don't remember exactly how big they are, but that boulder on the very far right edge that you can see, it looks like it's just kind of hanging on the end of it, the asteroid. An asteroid that size, or a boulder rock that size, actually was responsible for the airburst that occurred over Chelyabinsk, Russia, about 10 years ago in February of 2013, if you'd heard about that. Now that asteroid didn't make it to the ground, it just exploded in the air, but it still caused a lot of damage on the ground over where it exploded. So even those are hazards, not just solid asteroids that actually make it to the ground, but asteroids that explode in the atmosphere are also a hazard we gotta look for. Okay, great. Next one, next picture. So this is asteroid Vesta. It's the second largest asteroid in the asteroid belt. It's relatively circular compared to the others, most others. It and Ceres, which is the largest asteroid, are the only two that really are round. The rest are just kind of like that one, the previous one. You actually see craters on this one, as you point out. And you talked about the possibility of some area being young, a surface being younger than the other because it has less craters, and that's true. That the fewer craters a surface has, the younger it is than a surface with more craters. That's certainly true. One thing, I don't really think the readings went into this, but when that's done, when scientists date surfaces using crater counting, what they call crater counting, what they do is they take two surfaces that are the same area. So whether it's 10 miles by 10 miles or 100 miles by 100 miles, just depends on what the purpose of the research is. You take similar areas of surfaces, you count every single crater inside of it, and you measure the diameter of every single crater inside of it. And you put all that information into something they call an R plot that then gives you this slope, and that slope gives you an age. So it's not as exact as like actually having a sample and doing chemical analysis on that to get an age, but it's not bad. It's good for the purpose it serves. Okay, and next slide, next picture, or last picture. So this is a close-up from an asteroid named Eros, which has a very similar shape to that first asteroid that you looked at, Itokawa. Very similar in shape to that. Kind of looks like a dog bone, really. But there's a spacecraft that also went to that asteroid and got this particular image. Just for a sense of scale, the largest boulders that you see kind of on the left of center a little bit, those are about the size of a house. So this is kind of like looking down on a neighborhood in a satellite image. That's the scale of this particular image. And you can tell how, I think there in the readings, there was something about the Brazil nut effect. That idea that if you take an object that has various sizes of particles, like an asteroid, for example, or a box of cereal, and you shake it up enough, all the small particles will wind up at the bottom, and all the big particles will wind up kind of being at the top. And so that's something that's going on, we think, with the asteroids like this, these rubble piles. And you really can kind of tell that here, where if you look around the really big boulders, it looks like they're partially buried. You can kind of see the tops of them, particularly one of the larger ones towards the lower left near the edge. That largest one in that, you can really see how that's mostly buried, or at least partially buried. And so that's where that idea of the Brazil nut effect. So, all right, good job. So asteroids are very fascinating. We don't have a lot of information about them. We have samples from just a few of them. So we actually know, something about the composition of those asteroids. We have lots of meteorites that we know come from the asteroid belt, but we don't know exactly where they come from. There are a few exceptions where we're pretty sure we have some that came from Vesta. For the most part, we don't know exactly which asteroids they came from. Most other information we have about asteroids just comes from telescopic observations, which you probably read about, but those are fairly limited into what we can actually discern from those. We can still kind of guess a lot from them, which is actually pretty impressive. All right, I might have to turn off my camera just because it might start kind of doing this psychedelic thing. So if it does, I'll have to turn it off, and I probably won't turn it back on. That's the only reason why. So, all right, whenever you're ready. Go ahead.
So good afternoon, and thank you for taking the time to be here with us. This is our Moon 101 presentation from Mahopac Science Research Period 8. My name is Dan Walsh.
Mine's Luke.
I'm Braden. I'm Andrew.
So on this first image, we see various simple craters. And we know they're simple because of the shape of the bowl and their rim. And these simple craters are formed from small impactors because of their small size and round edges. So we see the bottom right crater is simple with another crater inside of it. We originally thought it was complex, but it seemed too small because the impactor was likely not large enough to create a complex. And then top left is likely the oldest formation in this photo because of how shallow it appears. And that appearance is likely because of accumulation of hardened lava and debris.
And we could, using that information that these are craters, we can determine that the light is coming from the left side to the right with that little arrow showing that. We also have like the mare, which we don't have an arrow pointing to just because it's a large section of it. It's made from basalt and hardened like magma and lava. The picture on the top is the site of the Apollo 12 landing, and we can see like what looks like to be footprints around the crater, and you can even see like a little like rover on like the top right side of the image. And that's about it for image 1.
So for image 2, there are a variety of different lunar surface features, most prominent of which is the sinus, I believe I'm pronouncing that correctly, the sinus rill, present in the center of the image. We know it is a sinus rill due to the curves that we can observe. And the sinus rill formed along with the lunar mare. The lunar mare is present in this image to the right and also to the top left. The lunar mare, like Andrew said, formed from hardened lava, and this lava was after there were many impacts upon the surface, there were like oceans of lava, and this lava hardened and created the lunar mare. And there were also tubes of lava that were present, and these lava tubes hardened and collapsed in on themselves, which create the rills present in the surface of the moon today. And the rills formed at about the same time as the mare, as all the lava cooled and hardened, making the mare and the rill the oldest features in this photo. There is also white color present at the bottom of this photo. We believe that this is likely caused by debris from various impactors, and we believe that it's mainly silica due to its white color, which is a compound of oxygen and silicon. There is also the presence of simple craters to the right of the image. Initially, they were thought to be possibly complex, again, due to their seemingly irregular shape, but we believe that it's likely that they're two simple craters in close proximity to each other. And the light is directly overhead. Initially, we thought that the rill was an elevated ridge, but once we determined that the light was coming from directly overhead, it became apparent that it was a rill. And that is everything for the second image.
And here in the third image, we have a variety of features present. We have mare, which is more like clearly seen in like the top left. We have another rill going through most of the image. I believe this is a Hadley rill. We also have a crater on top of the rill. And we have the lunar highlands to the right, which are composed of anthracite, and that creates high albedo as seen in the image. the highlands are the oldest feature that are present on the moon, but also in this image. You could tell that largely just based off the fact that they're the most almost impacted one. They're not as smooth as the mare, and it's because they've been around for longer and they've had more of a chance to get impacted. Then the mare were formed and along with the rill, but the rill were formed a little afterwards. As they said before, the mare were formed from that hardening of the lava, and the rill were those collapsed lava tubes. And you can see both the mare and the rill have craters along them. The rill is almost cut in half from one of the craters that's in the center. That one we think is a simple crater because of how smooth it is. Although it is large enough to be a complex crater, it looks a little too uniform and circular to be a complex crater. And the mare has a whole bunch of, mare and the highlands both have a whole bunch of small, simple craters along it that they seem really small, but this picture is just a lot more zoomed out than the other pictures. So the order goes, highlands were formed first from that hardening stuff that, like of crystals that came up to and floated to the surface. And then the mare formed after impactors allowed lava to flow up and harden. And then the rill formed shortly after that. And then craters came in after that. And that's all the features of that third image.
So that concludes our Moon 101 presentation.
Great, thank you. I do have a few questions. One comment I'll just say off the bat is you did a really good job of what we would say annotating, right? So you're pointing things out and then labeling it, right? You didn't have a lot of text cluttering up your slide, or not cluttering, but taking up a lot of space. And that's good. A lot of groups, particularly in these 101 presentations, because it's their first time really probably doing something like this, they tend to put a lot of text on it. And I'll tell you what I tell them is what that does is it distracts the audience. So if you're talking and saying something that's not written, what your audience is doing is looking at your slides, and they're looking at whatever you have up there. And if you have a lot of text, they're reading that and not listening to you. So if you're trying to communicate something important that's not on your text, on your slide, they're probably not going to hear it. So good job with that. Let's jump up to the first image, please. Okay. So yes, these are all impact craters on this image, and yes, this is the site of the Apollo 12. The Apollo 12 astronauts landed. How did you determine where the light was coming from? Or how did you determine they were craters, vice versa? I mean, they go hand in hand, right? Those two conclusions. How did you decide that?
Well, looking at like other images of, like, not just like this image, but like other images of the moon, like similar to this, they were craters, and then that's how we determined that they were craters. And then using that fact that they were craters, we were able to determine where the light was coming from based on the way that the shadows were and the way that the light was reflected off. Okay.
So you simply looked at some other pictures of the moon, saw what craters look like, and well, okay, yeah, great. And something I put down here from the third picture, but it applies to any crater. So you're talking about simple versus complex craters, and talking a little bit about like their morphology or how they look. But you talk about their size, like for example, in image 3, that larger crater that's called Hadley crater, about how it could be large enough to be one. And let me just say, on the moon, if something is large enough to be a complex crater, there is no doubt it is a complex crater. It will definitely have the characteristics of a complex crater. I don't remember if this is in your readings or not, but there is something that's called a transition diameter. Did you come across this?
I don't remember it.
Okay.
Offhand. It could have been mentioned.
That's fine. It's not really important, but it's useful. So a transition. So if you look at, Mercury, Venus, Earth, and Mars, and the Moon, and people have been doing this for years, counting craters, measuring crater diameters, Each planet or the moon has a point where we notice that craters stop there's a certain diameter where simple craters are no longer simple. Craters are complex. So of course, the larger they are, the more likely they are to be complex. Exactly what those diameter ranges are depends on the gravitational field of that object. So on the moon, for example, you can have much larger simple craters than you would have on the Earth, because the Earth is going to start, the gravity from the Earth will start modifying a crater's morphology, because it has at a smaller scale crater than the moon, because our gravitational field is so much stronger. So a useful thing you could use if you're wondering if something is a complex crater or not, and you can't really tell just by looking at it, you could, if you have a scale bar, for example, you can figure out its diameter and look and see what's the depth, what's the transition diameter for craters on the moon, and then you can see what that diameter is, and if it's greater than that diameter, it's a complex crater, and then something has happened that you can't really see that morphology. But all the craters you see in the pictures of these in these three images, they are all simple. So here you talked about one's a very old crater, and I would agree that that is definitely an older crater than some of them, like the more defined ones, like the one you point out there and you zoom in on the lower left. But just semantically, be careful using the word old or very old, because that implies somehow you know what the age of that one is compared to the others. But if you just say something like, this one is older than this one because it looks very filled in, that's good. That's okay. Just be very careful about kind of setting absolutes in the future. You know, just something to remember. Okay. Second picture, please. Mindful of time. Okay. Yeah, good here. This is a very high sun angle, like you say, because there's. How'd you come up with that? How'd you think that, or come up with that conclusion? This is a high sun angle.
We were looking at like any craters because from the first image, we were familiar with how the crater shadows respond to the sun angle. And looking at the simple craters off to the right of the image, they have a very small shadow, it looks like, and that shadow is closer to the center of the crater. It looks like it could possibly, the light even becoming slightly from the left, but mostly overhead based on those shadows.
Okay, yeah, good. Yeah, I wouldn't say it's directly overhead for the reason you just said, because there is somewhat a little bit of shadowing, particularly if you look at the rill, right? You can see on that left side of it. And it's sinuous. Sinus is close, but there's another U in there. So sinuous, yeah, sinuous rill is how you pronounce that. And yeah, that white stuff is debris. But I would caution about even being really generic in saying this is some kind of silicate, simply because this is just a visual image. There's nothing in here that gives you any indication other than color, which isn't very helpful, of a composition for it. It is certainly debris. I think you can very clearly make that argument. But another thing too is on the moon's a tricky place in terms of the because shades of gray, right? But the longer material sits on the surface of the moon, the darker it becomes. So it could be a very bright white rock to start with, but if it's been sitting out there since it first solidified, it can actually turn a very dark color. And they call that the maturity of the rock. Well, it actually happens more often with like the regolith, the dirt, than it does larger rocks. But just another thing that you may come across, depending on what your topic is that you do research on, this idea of the maturation or how mature the regolith is on the moon. So, okay, last image. You did a good job talking about the relative ages of those 4 main features in there. So good job with that. Other than the fact that the highlands are very rough and obviously have been bombarded quite a bit, what else do you know from your readings that tells you the highlands are the oldest feature seen in that picture?
We read about how they were formed, which is when the surface of the moon was mostly just like magma and stuff. And this first thing that solidified, the lighter stuff, floated up to the top. And I believe it said that almost all the moon was like kind of a highlands. They didn't call it that because there was nothing else to, like, you can't, if it's highlands, you kind of have something to compare it to. But that's just the first stuff that floated up to the top that solidified first was the highlands. So we knew that that would be the oldest one because that solidified first.
Okay, perfect, great. Okay, great. All right, well, that's all I got. Thank you.
Thank you very much. Have a great rest of your day.
Thanks. You got another one up.
So we're actually going to swap out, and the other kids are going to do the asteroid. So why don't you guys log in, grab that link from Classroom if you didn't already, and come on over here. They heard everything that they were saying. They were just kind of sitting on the sidelines so that there wouldn't be as many kids in the Zoom at once. So they will be here and logged in momentarily. Hit launch meeting, guys. Start the process. Then once you get in, just make sure your camera is working. If it's the ceiling, you have to go down to where it says stop video and change it. I feel like Zoom changed some of its settings since we used it last. So it keeps giving us like different messages and things we have to do.
You never know.
Mm-hmm. So some of the kids are having trouble with their cameras working at all. So I think maybe just in the interest of time, we just get started, and like Nate will have a blank screen and hopefully Cass will figure it out.
Yeah,
but it might be easiest. Yeah.
No worries.
So guys, why don't you go ahead and share your screen, whoever's gonna be the screen sharer.
How do I share my screen quickly?
On the bottom, there should be a share screen. I think it's in green. Okay. Who knows? It's not a big deal.
Doesn't even allow me to turn mine on.
Okay, so if your camera's not on, it's okay. When you're speaking, you can unmute yourselves, but you also want to make sure your speakers are turned off. Okay.
Can everyone see my screen?
Yep. And is it good for them to just start whenever they're ready?
Oh,
I think you can go. Yeah. Are we good to go?
I can't
Yeah. Okay.
audio without.
Hi, and welcome to our Asteroids 101 project. My name is Giovanna Perillo.
My name's Hayden Bielchini.
My name's Cass Fabi.
My name is Danica Parent.
And my name is Nathan Maskell.
I'm sorry. Is somebody speaking? Because I don't hear anything. Can you all hear me?
Were you able to hear that, or?
I heard intros and then it went to this slide and I heard nothing after that.
Go ahead.
Today we're going to start with some background information. I'm going to start with the four categories of asteroids. The first is a C-type asteroid, which has a generally low albedo and accounts for about 75% of all asteroids. S-type asteroids are relatively bright and have a moderate albedo and account for about 20% of all asteroids. M-type or metallic asteroids have a high albedo, and V-type asteroids, which are also called Vesisoids, have a spectra similar to that of the 4 Vesta, which is part of the Gemini constellation. And these account for 6% of all asteroids. Two effects that we're going to be discussing today is the Brazil nut effect, which occurs when large irregular shaped particles combine with surfaces of granular materials. These can be like asteroids. The other is accumulations, which is the gathering of particles by gravitational forces to a large object in space, such as asteroids.
Next, we're going to be talking about what the different categories of asteroids have in common. They have a semi-major axis, which is like 1/2 of the major axis of an elliptical orbit. It's also the mean distance of that orbit from the sun. They have eccentricity, which is how they measure how non-circular the orbit of a body is. If it's really eccentric, it's almost a perfect circle. Orbital, they have orbital inclination, which measures the tilt of an object's orbit around the celestial body. And also they have spectral features, which astronomers use spectral lines to determine not only the element, but its temperature and density of that element on an asteroid.
Next is what generally holds the asteroids together. So for smaller asteroids, they are related to how the atoms and molecules, the forces that holds them together. So smaller asteroids are predicted to get weaker as they get larger, and they're held together by their material strength, which is their ability to withstand an applied load without failure or deformation. For larger asteroids, they will get stronger as they get bigger, and they are held together by gravity as long as the centrifugal force is not strong enough to overcome the gravity. And the centrifugal force is it's an imperative force that acts outward on a body moving around the center and arising from their inertia. And just extra for what holds them together, researchers have also found that cohesive forces or friction help to hold some asteroids together, especially when there's loose rocks or boulders on the surface.
This is an example of a S-type asteroid. S-type asteroids are found in the inner asteroid belt, approximately 2.2 AUs from the sun, and they are moderately bright and consist mainly of iron and magnesium silicates. They're approximately 4.6 billion years old, and were created during the creation of our solar system. And the large boulders found on these asteroids were created because of the Brazil nut effect.
This asteroid has impact craters below albedo and it's a C-type asteroid. As Giovanna mentioned before, a C-type asteroid is made of carbonaceous materials, and they were formed at lower temperatures in the outer part of the asteroid belt. And lower albedo can make the asteroid extremely dark and incredibly hard to locate, so more advanced equipment is needed to study them. And the impact craters formed on the surface of the asteroid come from high velocity impacts with the asteroid that make the craters. And C-type asteroids were formed in the early formation of the solar system over 4 billion years ago.
Asteroid 3 is a C-type asteroid since it has a low albedo. Again, there are large boulders present, and these are formed from the Brazil nut effect or accumulations. These asteroids are formed from collisions with early solar system other asteroids and planets, and are the oldest asteroids compared to the other types of asteroids. They also are approximately older than 4 billion years old. I believe that is our presentation, and thank you so much.
Hey, thank you. So I guess one thing I'll just mention that you probably don't need to, based off my comments from the first presentation, is a lot of text, particularly early on. The one suggestion I would have is, so like on the first slide, you talk about the different types. And I'm thinking you had a box about the Brazil nut effect and then a box about accumulation. What I would do is, instead of that text, have pictures of each of those types and then label it. Then you just talk about it, right? Same thing with the Brazil nut effect. Have a picture of an asteroid that shows that or exhibits that, and maybe even like, can you all think of something like that happens every day on Earth, or that effect takes place? Probably takes place in your pantry. When you're getting in a box of cereal, where are the crumbs and the powder?
They're at the bottom.
They're at the bottom. The big whole pieces are at the top. Yeah, that's the same idea. It's the same thing. So yeah, so you can have some kind of like example, everyday example of that, you know, something like that. And speaking of the Brazil nut effect, just to clarify, so the Brazil nut effect isn't what formed the large boulders you see, for example, in that first picture. That is the process that's responsible for having the boulders near the top or near the surface, because those kinds of asteroids are what they call rubble piles. And so like you said, like you talked about how it's just a bunch of rocks and dust that's really kind of loosely held together by gravity, and then to some extent, you know, electrostatic forces too, particularly on a small scale dust. So if an astronaut were to go to that thing and just put their hand on it, it would start coming apart and then just come back together again over time. So yeah, so impacts occur that shake those things up, especially early on, and may even tear them apart and bring them back together again, or those randomly pieces come back together again. But ultimately, that's what brings those big boulders to the top, is this idea, this Brazil nut effect. For each of your 3 asteroids, you gave them a type. You identified it as a certain type. And how did you come up with that classification for each one?
So we did a little bit like more research on like how to identify like how from looking at the images how to identify the asteroids. What we came up with was that I believe S-type asteroids had the lowest albedo. So we looked at the albedos of each asteroid, and that's how we determined the effect.
Okay, fair. So albedos, of course, I don't want to say of course, albedos are measured by how much light gets reflected off of them as seen by like a telescope, right? Because when you look at a picture of an asteroid, especially those, no, in particular the ones that we're looking at, because those were all taken by spacecraft that are right there, taking pictures of them. The lighting is all kind of adjusted, so they all look the same brightness, kind of. I mean, kind of hard to tell, with some exceptions of shadowing and that kind of thing. But the idea is right. You're right. The idea is how bright they are. How relatively bright they look. The second image that you looked at, that's actually a picture of Vesta. So that's I guess in this case would be a V type. It's the original Vestoid, right? The OG of Vestoid, so to speak. And the first asteroid was Itokawa, which we actually have samples from. An asteroid visited that about 20 years ago, brought back samples. Vesta was the second image. The third image is a very close-up shot of the asteroid Eros, which kind of looks like a dog bone if you see an overall picture of it, but also a rubble pile like Itokawa. And in that particular image, for a sense of scale, the larger boulders that you see are about the size of a house. So that's kind of like looking down on a neighborhood, to give you an idea of how big that area is in that picture. So,